Got it. Let me get this. Okay. Yeah, so welcome. This is just an intro slide about myself. We always start with these in my department, and Craig just went over my academic background. The PhD that I'm working on finishing over these next couple months is sort of a mix of geosciences and geography mixed in with some political science, gender studies, and critical theory. So I'll get back to that later in the presentation because the interdisciplinary nature is where I like to work. Outside of academia, I have 20 years experience in political and social justice organizing, which also feeds into a lot of how I think about climate change and how I work on it, and how I approach my research. Things that I just enjoy for fun are biodiversity conservation, trying to reestablish native species in my yard and document the return of native pollinator species. It's what I like to do for fun, and mental health and gardening. I'm also first generation student, queer and chronically ill, so have not always had the easiest path through my academic studies because of that. And I also really like to dance. So that's a little bit about me. And this talk today is sort of 4 different parts, and I just put them all together. Sorry, was there a question? Or maybe someone's just unmuted. So I'll go through 4 different sections. The first part is from my first publication that was about Antarctica's impact on future global climate under high emission scenarios, looking at freshwater forcing in a global climate model. The second piece that I'll go over is a little bit of the new Nature paper that Rob led that came out in May about sea level rise commitments under the Paris Agreement. And that had, there was a piece of that I worked on, and also I refer to that paper in part of my dissertation to assess the climate justice considerations of sea level rise under the Paris Agreement. Then the third part will be on assessing ice sheet climate feedbacks using coupled climate and ice sheet models. So that's what I've been working on for the past year, and I'm going to show you some extremely preliminary results from that, and then update you guys on it later as that work progresses. And then the fourth part of the project will be the chapter of my dissertation that's on the climate justice implications of the spatial and temporal variability of sea level rise and how that interfaces with UNFCCC negotiations and the Paris Agreement. Okay, so section 1. The central focus of my dissertation starting out was on trying to assess how Antarctic melt will impact other parts of the climate system, such as global temperatures and ocean circulation, because Antarctica plays such a central role. And I always like to show this figure, which is just a Spillhouse projection, showing how depending on how you look at the world and how you consider it, Antarctica can be very central to the climate system, as you're all very well aware since you're attending this seminar. So this work was first, we published this in 2020, but I actually started working on this section of my dissertation much earlier. So this was initial work that was done in like 2016 and showed at AGU in 2017. And then there was a long road to publication. And so I'm really glad that this is finally out there. It's my first author publication. So just to center ourselves for a minute, I know you've all seen these same images before. But this is just looking at the Antarctic ice sheet and how the bed is a unique configuration between East Antarctica and West Antarctica, where various portions of it are grounded below sea level, especially in the West Antarctic ice sheet, but also in portions of the East Antarctic ice sheet as well, which leave it very vulnerable to warming of the ocean waters. And there's observational evidence, of course, that processes such as marine ice sheet instability may have already been initiated at several sections around the ice sheet. And this is just looking at the velocity field on the right. So The models that I used for this study were a combination of the community Earth system model, fully coupled global climate model that incorporates land, atmosphere, ocean, sea ice modules, and then a stub ice sheet, which I actually mask out, and I'll go into that in a minute. And then the Penn State University 3D ice sheet model, which is capable of simulating marine ice sheet instability and marine ice cliff instability, which I know some controversy on that process and implementation, but we stress that it is observed at Jakobshavn Glacier and that this could be an increasing issue going forward in the coming centuries, as especially under high emission scenarios. So this work was using the freshwater forcing, the ice sheet melt quantities predicted in the DeCanto-Pollard 2016 paper, and using those to force CESM to try to get a more realistic assessment of the spatial and temporal variability of freshwater forcing. So basically what I did was interpolate the ice sheet model melt onto the CESM grid and then move it to the nearest ocean grid cell, keeping the liquid and solid components separate so as to account for latent heat. And then altering the source code for CESM in the coupler to mask out the melt that CESM would internally calculate from the ice sheet that's inherent in CESM, and then replace it with what was being predicted from the DeCanto-Pollard melt. And this is important because, as you're probably all aware, CMIP 5 models tend to underestimate the amount of melt coming off of the ice sheets. And we'll see that in a couple of slides, what the CESM estimated meltwater forcing is versus what the DP16 meltwater is. And so these simulations are run not coupled. I took the full span, well, up to year 2250 of that ice sheet model prediction and fed that all into CESM. And so nothing is parameterized in the freshwater forcing here. It's all going in exactly as predicted by the ice sheet, both in terms of space and time. So the meltwater is changing year to year. There's no imposed seasonal cycle. We considered it, but we didn't do it. So it's varying annually, and then it's varying around the continental margin. And so after I've done these steps of interpolating the ice sheet melt onto the CESM grid, moving it to the nearest ocean grid cell to assure that it's all going into the ocean, or everything that would be going into the ocean is, this is what the freshwater forcing field looks like. Just for an example year, this is the year 21-25. So after things have really started to pick up. And so, yeah, that's what it looks like. And I also want to note that this freshwater forcing is all happening at the surface layer. None of it's going in at depth, but as a paper by Pauling in 2016 showed that there wasn't much of a difference when you did input the freshwater forcing at depth. So we think that it's a reasonable assumption to have it going in at the surface. Also, the methodology that I'm using doesn't allow for us to input it at depth. So all of the freshwater is going into the surface, liquid and solid components are staying separate, and then spatial and temporally variable. This is supposed to be a movie, but it's not playing. So I'll just stay here for a second and say that you can see the spatial variability of the sea surface salinity response in response to where the freshwater input is going in. And okay, this one plays, interesting. And then we have sort of different things that are happening. So we have the response in the sea surface salinity field, and then we have the response of the sea ice, because dropping the salinity is allowing it to be, allowing sea ice to form more easily on the surface. That then induces an albedo feedback, basically exactly the opposite of what we're seeing in the Arctic today, where sea ice starts to expand around the continental margin. Then the albedo feedback kicks in and we have a delay in the surface air temperature response. However, simultaneous to that, we have increasing stratification of the water column due to that freshwater cap. And so the warm water is being sort of just captured down there at depth, where it's able to impinge upon the grounding line. But of course, since this model is not coupled, the ice sheet does not know that this is happening. This is all just CESM response to a freshwater forcing that's been applied. And then later in the talk, I'll discuss what we're doing now to do the coupling. So you can see here, this is the anomaly in temperature at 400 meters water depth, and this is the sea ice thickness growing around the continental margin over time. And so this is one of the main figures, figure 1 from the paper, that's just showing that the freshwater forcing in comparison to the 2-meter surface air temperature. And so what we have here is RCP 8.5 on the left and RCP 4.5 on the right. And so let's just go through this for a second. The solid lines are the meltwater perturbed runs, and the dotted lines are the control simulations. So control has no freshwater forcing perturbation added. We're just letting CESM do what it does without masking out the CESM response. So this dotted line at the bottom here is the CESM predicted amount of freshwater forcing coming off of the Antarctic ice sheet over the coming years. Very, very low, versus the solid blue line, which is the freshwater forcing predicted from the DeCanto-Pollard 2016 paper from a dynamic ice sheet model. So pretty vast difference between this amount of freshwater forcing and this amount of freshwater forcing. And we can see how due to the growth of sea ice, that has a large impact on the surface air temperature. So the dotted line in black is the surface air temperature response globally, not just over the Southern Ocean, to this predicted freshwater forcing, or just the surface air temperature response in general. Whereas the solid black line is the surface air temperature globally under the freshwater perturbed run. So you can see that it's still, of course, increasing. This is an RCP 8.5 run, so of course it's increasing, but it's increasing at a slower rate. And so there's a pretty big difference between the surface air temperature response in the freshwater forcing run versus the control simulation. And there's especially at this point of large scale collapse of the Ross ice shelf, where we have a huge amount of freshwater coming in all at once, and the surface air temperature actually like dips for just a little bit there and then starts increasing again. So that is what it looks like under RCP 8.5, where we have a catastrophic collapse, versus RCP 4.5, where we have the same basic situation, but at just a lower version of it. So again, the control run freshwater forcing prediction is this dotted line at the bottom. The perturbation freshwater forcing is this steadily increasing blue line over here. And then the surface air temperature response of the control is the dotted black line, and the surface air temperature response of the perturbation run is in black, the solid black. And so this shows us that the freshwater forcing is going to have a large impact on global climate. And especially I was interested in the surface air temperature field because the Paris Agreement is defined in terms of surface air temperature. So it's interesting to see what this impact would be, because you have these two dual things happening of a negative feedback on global mean surface temperature and simultaneous increase in sea level rise, which we'll return to in part 4 of the presentation. And in the paper, we go through more fields than just this. We talk a little bit about AMOC and Arctic sea ice and several other factors, but I was just going to show this one section for today. So moving to the next piece, which is sea level rise under the Paris Agreement and how this meltwater perturbed climatology could impact ice sheet stability. This is from a paper that was in the works for several years, and I was really excited that it was finally published this past May, led by Dr. Rob DeCanto, with this amazing team of people who all contributed immensely to this project. And so this was an honor to be on. So I'm just going to talk just a little bit about the main figures and then the piece that feeds into the work that I just showed. And so these are the first 2 panels of figure 1, just looking at possibilities for sea level rise contribution just from the Antarctic ice sheet, not total sea level responses just from the Antarctic under the Paris Agreement. And as you all know, that the Paris Agreement is defined in terms of global mean surface temperature with a stated goal of 2 degrees Celsius, limiting temperature rise to 2 degrees Celsius above pre-industrial, or a reach goal of 1.5 degrees, staying below 1.5 degrees above pre-industrial. And so this global mean sea level contribution from Antarctica is fairly similar under both of those Paris Agreement goals, the 1.5 and the 2 degrees, 1.5 shown on the top panels here, and 2 degrees shown at the bottom. So it's only like 0.01 meters difference at 2100 and 0.06 meters difference at 2300. But we know that every bit of sea level matters, especially for locations that are most vulnerable, such as atoll states. And if you notice in the column at the left, that's for the current century. And while the Paris Agreement doesn't explicitly mention the year 2100, that's the main point of temporal reference that's generally associated with it, which means that we end up talking a lot about the current century. But to really grasp the extent of impacts, we need to look farther, and we need to consider intergenerational equity and justice concerns. So looking at the column on the right, we can see these same projections out to 2300. And this really drives home the point that even under 1.5 C, we will not be able to prevent a full meter of sea level rise in the long term. Under both 1.5 C and 2 C, we have a multi-centennial commitment to at least 1 meter of sea level rise. And then it's important to consider what happens if we surpass the goals of the Paris Agreement, because of course we're not anywhere close to being on track to meeting them. At this moment, NDCs submitted, or at the time of the paper being written and this work being done, NDCs were on track for 3 C of warming, and they're still on track for greater than 2 C of warming by the end of this current century. At 3 C, we get a significant jump in sea level rise contribution from the Antarctic ice sheet. And then under RCP 8.5 scenario, which is significantly worse, there could be 10 meters by 2300 just from the Antarctic contribution alone, which is fairly unimaginable. The plot on the lower right is showing the main ensemble and how it compares to the freshwater forest climatologies. I'm going to return to this in a couple of slides, but I just wanted to show these figures for a second, showing that under 3 degrees C, we do have a significant jump when 1.5 and 2 degrees were fairly similar in terms of sea level contributions. Once you surpass the goals of the Paris Agreement, you start adding on sea level contribution fairly quickly. And then considering the impact of carbon dioxide removal was another piece of this paper. And so another aspect of the Paris Agreement being defined in terms of global mean surface temperature is the normalization of overshoot pathways and negative emissions technologies as being acceptable solutions for meeting the long-term temperature targets. And of course, many people have raised many concerns about the normalization of overshoot pathways, but this is something that is very much normalized within discourses in the scientific sphere and in the policy sphere. But sea level, of course, cannot be drawn down in the same way that global mean surface temperature could be. So we need to look at how negative emissions through carbon dioxide removal could play out for the ice sheet. And under the 3 C pathway, which we're currently on with the NDCs, we modeled that with carbon dioxide implementation starting at each decade. And this image shows the equivalent CO2 trajectories for, and the second one shows the global mean sea level response of the ice sheet. So we can see that after 2070, there's a really large jump in committed sea level rise. And so this is going to show that unproven and undeveloped negative emissions technologies are not going to save us from ice sheet induced sea level rise, marine ice sheet instabilities. The only real option for diminishing the contribution from sea level rise is to have strict near-term emissions reductions and to keep oil and gas in the ground instead of burning it into the atmosphere. So this is just showing you CDR implementation starting at each decade after 2030. And then this is showing the equivalent CO2, and this is the global mean sea level response. You can see that after 2070, there's a really large jump in that contribution. So once those instability points are breached, sea level rise is committed. We're not going to be able to restabilize the ice sheet in some sort of manner. And this also really shows the importance of looking long-term as well. So all of these scenarios with carbon dioxide removal following that 3C trajectory exceed 1 meter by 2500. And no scenario shows any sort of recovery of the ice sheet, even those that return to a near pre-industrial level of greenhouse gas concentrations by about the year 2300. So we optimistically tend to assume that CDR technologies will be capable of reducing atmospheric CO2 atmospheric mixing. But even with CO2 and temperature declining, once MISI begins, it's really unstoppable. So yeah, even with early implementation, even with successful implementation of carbon dioxide removal, sea level rise of 1 meter is still looking like what would be the possibility. And of course, just a reminder, this is just for Antarctica. This is not including thermal expansion. It's not including Greenland or other glaciers. It's not yet. So it's a lot. So while the concept of overshoot could work for temperature, it does not work as a concept for sea level. So now we're going to return to the plot from figure 1 that I showed earlier that included the ice sheet response to freshwater perturbed climatologies under RCP 8.5. So we did an initial assessment of the dual feedback, those dual feedbacks that I showed from the Antarctic ice sheet earlier, where in my freshwater forcing perturbations, we had that increased heat at depth in the ocean, but we had the delayed surface air temperature due to the sea ice growth at the surface. And so it was trying to figure out like which of those is going to win out in terms of ice sheet stability. Is it going to be the increasing temperature at depth, or is it going to be the decreased surface air temperature, which could prevent some of the hydrofracturing? And so you can see here that with meltwater feedback, we're following the blue line, and then without meltwater feedback, we're following the red line. So this is my control simulation that we showed earlier, and this is the meltwater perturbed simulation. So you can see that overall, the meltwater perturbed climatology had a negative feedback on ice sheet melt. So the ice sheet stayed stable a little bit longer under the freshwater forcing. So the meltwater feedback delays and lowers the sea level impact, though it's still over 5 meters by 2250. And the response to the two climatologies tends to diverge around mid-century. And so what we want to look at next is what happens if this coupling works both ways. Because when I do the freshwater forcing in CESM, I was just feeding in that meltwater prediction from the ice sheet model. And then when we do this, we're just feeding in the climatology to the ice sheet. But obviously, they're going to respond differently if they're responding to each other simultaneously. And so what we really want to know is what's going to happen if the ice sheet knows what the climate model is doing in real time, and if the climate model knows what the ice sheet model is doing. Okay, so that is where we're at currently, and this is extremely preliminary work. So this is what we're doing next. I have CESM and the Penn State University 3D ice sheet model currently in an annual two-way coupling. It's been a heck of a thing to try to set up and to get working well. So what we're trying to do is match melt rates in key regions to observational values. And this is just a plot from Edumusili, the 2020 publication showing melt rates around different regions of the ice sheet. And what I am trying to do is match the observational rates as well as I can for the early years of the simulation from 2005 to 2020 under an RCP 8.5 pathway in CESM. And it was proving a bit difficult because CESM is the ocean circulation at depth is extremely sensitive to freshwater input. And so I ended up having to have a little bit of a compromise in trying to match the melt rates. I can't get them all exactly to observational around every part of the ice sheet. It ends up being that Pine Island and Thwaites melt is a little bit underestimated in order to keep the Ross and Weddell sea basal melt rates approximately at observations. When I bump up the parameters to get Pine Island and Thwaites up to observational values, I end up with too much basal melt in the Ross and Weddell seas. And then when that goes in to CESM, it ends up causing the ocean circulation to collapse a little bit too soon and the heat to build up at depth a little bit too soon. And I was getting these runaway positive feedbacks in which the ice shelves were collapsing within decades, which is obviously not physically realistic. So this is what I'm trying to do right now, is just sort of skirt that line of getting everything approximately to observational, but keeping these basal melt rates under the shelves low enough so that when the meltwater goes in to CESM, it won't cause that sort of runaway feedback effect. And of course, this is all complicated by the fact that CESM does not have cavity circulation under the ice shelves. And so when I'm passing the CESM climatology to the ice sheet model, I'm passing in the water temperatures that are at the edge of the ice shelf because there's no cavity circulation, and then those are being interpolated backwards under the ice shelf to calculate the basal melt rates there. So if the ocean's temperature collapses too quickly, this heat builds up too fast, then that gets interpolated back under the whole extent of the ice shelf, and the melt rates increase, the freshwater increases. It's a whole thing. So this is what I have currently, and the ice sheet output is on the left, and then the CESM input is on the right. And so these are a little bit hard to see because they're just point source melt. And so you can see Pine Island and Thwaites, darker areas there, very, very light shading under the ice shelves because those melt rates are so low. They're very close to zero. And then the methodology is the same as what I did with my 2020 Science Advances publication, where I'm taking the melt, I'm interpolating it onto the CESM grid. And so obviously there's a large change in resolution there because the ice sheet is extremely high resolution, but CESM is on a 1 degree ocean. And so in going from 20 kilometers resolution to a 1 degree resolution, there's a lot of ice sheet grid cells that are being combined into one CESM grid cell. And then that melt is being moved to the nearest ocean grid cell to make sure that it's actually entering where CESM thinks the ocean is, because if the melt is occurring over here under the ice shelves, but there's no cavity circulation in CESM, then CESM would not know about a basal melt happening here unless I move it to the edge. And so this is what this input looks like, again, spatially and temporally variable on an annual basis. And so you can see the higher melt rates here and then relatively low around the east margin. This is just to look at how the discharge rates, the freshwater forcing overall quantities is comparing to our previous work. So the blue line here is from my publication that I showed in part 1 of this talk, and the red line is from this new coupled simulation that I'm running now. So a few things to note: the overall discharge is certainly much lower. The initial melt is much closer to observational values here. You can see it was a little bit too high before. And that's because the pace of atmospheric warming was a little bit off in the DP16 paper. So warming was happening a little bit too fast and melt was being overestimated early on. That was due to an assumption made about the lag between CO2 and GMST. So in the 2016 paper, there was an imposed lag, and then this was then later fixed in the ice sheet model forcing that was used for the Nature 2021 run, and you could see that in the earlier images showing those results from the Nature 2021 run, where it's not happening quite as fast as before. So we saw that on the earlier slides. And so now in the new ice sheet configuration, without that with the lag corrected, the ice sheet predictions are aligning much better the atmospheric forcing is aligning much better with the CMIP5 predictions. And so we also see here, the third thing is that there's just really, really high interannual variability in the amount of freshwater discharge that's coming off the ice sheet. And so there's a lot of differences here, and we're not yet sure whether this is due or to differences in forcing or to the coupling itself. So that's something that we're going to try to tease out, because the forcing here is much different. In the DeCanto-Pollard 2016 paper, the ocean forcing is from CCSM4 and the atmospheric forcing is from an RCM. Whereas in the new coupled run, everything is from CESM version 1.2. And so there's just a lot of differences between these two lines, but I wanted to show that the overall melt rates are much lower and much more variable than what we had before. And so I mentioned that this work was preliminary. It is extremely preliminary in the sense that this simulation is currently running, and I just downloaded some data over the weekend and yesterday to plot up some initial results for you. So we have not been able to do a lot of analysis on this yet, and I'm just going to show you the broad ideas. And so looking at this interannual variability, like I said earlier, there's two components to the freshwater forcing, and I'm keeping liquid and solid components separate when it goes into CESM. And so this is showing that the interannual variability is driven by the solid component of ice sheet discharge. And so the ice sheet fields that are going into the solid component are calving and cliff failure, whereas the liquid components are the basal melt rates, cliff face melt, percolation to the base of the ice sheet, and then counteracted by any basal refreezing that's happening. And so this is just looking at the liquid component in the prior simulation is shown in the blue with the circles. The liquid component in the coupled simulation is the red with the circles. And so those are relatively similar, but basal melt is increasing quicker, probably because the ocean response in CESM is really sensitive. And so the freshwater forcing is causing a pretty rapid change in the ocean temperatures at 400 meters water depth. And then the solid component in the prior run shown with these little vertical pluses, and then the solid component in the new coupling run shown with the red with the pluses. And so the solid discharge was always the dominant component over the liquid, and you can see that in both the old simulation and the new, though they're much closer in the coupled run, the amount of discharge from the solid component and from the liquid component, but you can see the interannual variability there is from the solid ice discharge. So it's either calving or cliff failure, and it turns out it's actually both. And so summer temperatures over the Southern Ocean are driving a lot of these brittle processes. So we have the solid discharge is correlating with summer DJF surface air temperatures, but the annual values are likely not all that matters. We think that the spatial pattern of warming is having a significant control over the high melt years, and precipitation is also a factor as well. But like I said, this is preliminary results as of yesterday. So haven't gotten to dig into this as much as I would have liked in advance of this presentation. But if people have thoughts on this, please let me know at the end. Because yeah, I think one thing that I don't have a plot of in this slide, but there is a lot of calving that's happening around Wilkes Basin. And so when I took just a preliminary look at the surface air temperatures over that region, the warmer air is closer to the ice sheet margin in that one particular area, which is leading to more surface melt, and then leading to meltwater induced crevassing, and then leading to calving, and some initial cliff failure is starting in that region. And so that's what makes me think that the spatial pattern of warming is likely having a lot of control over this in addition to just the interannual variability, and trying to tease apart where the spatial, where the summer air temperatures are warming quickest and how that varies year to year, and then how that matches with where surface melt and brittle processes are occurring is something that I really want to look into as we dig into more of these results. And this is just looking a little bit at the more of the fine scale components instead of just showing you the liquid versus solid and how that freshwater is looking. This is looking at the individual components. And so the highest variability is in the cliff failure and the calving, which of course surface melt drives both, but the surface melt is not included in the CESM liquid forcing field because it would not necessarily enter the ocean. So that's not included in the freshwater forcing. Basal melt is increasing the quickest, and that is due to that rapid response of the deep ocean, especially near the larger ice shelves. The Ross and Waddell sea 400 meter ocean temperature is just very, very sensitive in CESM. And so here we have the cliff failure in orange, the calving in blue, the surface melt down here in green, and then the basal melt in this more purpley color. So definitely increasing the quickest due to that sensitive ocean, but really, really high, not as high variability, obviously, in the basal melt, but higher variability in the fields that are responding more to that surface air temperature and that change in summer surface air temperature year to year. And so this is all very preliminary work in progress. It's going to take a lot of effort to sort of dig into everything that's happening and to how much of it is due to the coupling itself, and how much of it is due to other changes in the way that we're forcing this ice sheet versus how it's been used in prior studies. And so I'm excited to look into this a little bit more, to try to constrain what exactly is happening here. But yes, if folks have thoughts on things that you would like me to look into and to update you on in a future talk, just let me know.
Can I interrupt you there 1 second?
What's that, Craig?
Can I interrupt you there 1 second? There's a question in the chat from Laurie Padman. Yeah, associated with this slide, perhaps.
Oh, sorry, I can't see the chat.
I'll just read it. Where around Antarctica is the main flux from cliff failure?
The main flux from cliff failure, so it's varying as the run progresses, and since I've only looked at a few time slices, one of the time slices that I was looking at over the weekend was in the 2030s, and there it was happening in Wilkes Land at sort of the East Antarctic margin. I'm not actually seeing a lot happening yet in Pine Island and Thwaites, which we definitely want to look into why that's happening. Those places have been more stable so far in the coupled run than the east side has been, and it's a little unclear about why that is so far. But yeah, that's a really good question. I'm seeing mostly the cliff failure response happening in the east.
This plot you've got up here looks really interesting. It looks like a lot of the more rapid melt seems to begin after around 2040, after this sort of like quite large cliff failure event.
Yeah, this guy right here. I haven't looked at that specific event yet, but I do think that since that's close to where I was looking before, I think that's likely driven by the east as well, by Wilkes Land. But yeah, as to what exactly is happening that's driving it, I'm not sure yet, just because we haven't had the time to look into this as thoroughly as I wanted to. Best plans of signing up for an August time slot, thinking for sure I'll have this simulation done and all of the preliminary results ready to show, and then did not account for Cheyenne being down for maintenance for a week, that then pushed back the whole simulation. And yeah, I would love to give you a better explanation for exactly why that specific event is happening, but it'll have to happen at another time.
Well, it's good for us. I can always get you to do another talk.
Thanks.
Oh, there's a question from Michael White. Any chance you'd like to unmute and ask a question, Michael? Just to pick on you. Sorry to pick on you.
Oh, yes. I may have missed it, but do your models account for feedbacks, like albedo change and methane release?
The main feedback that we're trying to assess is the albedo feedback in the Southern Ocean. But yeah, the model, the CESM does account for albedo feedback for sure.
But not methane.
Methane, I'm not sure about because that's not something I've ever looked into personally within CESM. But albedo feedback for sure. But that's a really good question about the other feedbacks inherent in CESM and how CESM accounts for methane feedback. It is actually a couple.
I don't understand the question. Methane feedback? Like methane being released by the melting? I don't understand the question here. Or are we talking about its concentration?
I thought he meant permafrost release.
Right. Yes, the latter.
Oh, surely they have. I mean, they
permafrost?
prescribe their greenhouse gas concentrations in so much as they have some sort of RCP scenario that has additional methane.
Yeah.
Do the RCP scenarios have additional methane release associated with warming? Like natural sources, not being produced?
I think it's what she just said. The concentrations are set within the RCP forcing, but I'm not sure about permafrost, like additional methane from permafrost release. I don't think is included, but I'm not sure about that.
Hmm.
I think that was what he was meaning.
Yes, thank you.
Thanks, Allegra.
I think this is super exciting. So happened my interns actually, their project over the summer was to look at the GIST model and the principal things related to surface mass balance and surface energy balance in some of our simulations. And they did a random forest regression to see which things lined up best with predicting surface mass balance. And it, in the GIST model anyway, it is the T surface on land ice. That's the most important feature, which is what you just said. And the next most important feature is the snow height. So it would be cool if you would do a similar kind of analysis to line them up and see, compare and contrast, see how they do.
Yeah, send me an email. I'd love to see the work that you guys did.
We have a clarification from William Lipscomb. Is there any chance you'd like to unmute quickly?
Oh yeah, I was just confirming what was said, that all the greenhouse gas concentrations are fixed in our CMIP scenario runs. But there are people who've used CESM to study permafrost thawing, and there is a biogeochemical model in CESM. So you can run the model with transient greenhouse gases, but that would be a special study, not a standard CMIP run.
Thank you.
Thank you. Would you like to continue?
Okay, one more
sorry,
section.
I wouldn't worry if we go a little over time here.
Okay, yeah, I only have a few slides for the last section because I wasn't sure how much to say of it. Okay, so the next section is on the climate justice implications. So this is going to be totally different from the rest of the talk. So like I said at the start of this presentation, the way that I sort of like to operate is in a more interdisciplinary manner. And so my initial work for my PhD was all physical science-based modeling work with CESM and with the freshwater forcing. But as I've done my PhD, I've also tried to bring in some of my background in social justice organizing from outside of academia, where I've been involved in various social justice and human rights organizing work for the past 20 years. And I've sought to sort of diversify the classes that I've taken and the people that I've worked with during my time in my PhD. And so that's meant taking classes in political sciences, in human geography, in gender and sexuality studies, in critical theory, and then trying to bring that in to my modeling work and sort of bridge the two. So this section is an interdisciplinary look at bridging the physical sciences with the social sciences. And this is a chapter of my dissertation that has become truly vast. I'm going to try to summarize an 11,000 word dissertation chapter with 200 references in the next 3 slides. So it's just going to be the broadest overview. But this was sort of something that I started thinking about after I did my first chapter of my dissertation, where I was looking at, the sea level rise predictions in DeCanto Pollard 2016 were very high. And then the surface air temperature response within CESM to that freshwater forcing was quite significant. And so it got me thinking about these dual impacts of Antarctic ice sheet melt, where you have sea level rise, but the sea level rise is happening simultaneously to a negative feedback on global mean surface temperature. And so what are the climate justice implications of that in light of the fact that the Paris Agreement is defined in terms of global mean surface temperature? And this is not an easy thing to try to constrain. And so some of my motivations for this is a paper that 2 of my friends, Emma Colvin and Marcus Thompson, wrote about bridging the divide between human and physical geographies and sort of thinking about potential avenues for collaboration on climate modeling research. And I was like, well, okay, I can do that. I have these 2 backgrounds. I can bring them together and make something of it and use my own climate modeling work to try to sort out justice implications. And then I hosted a session about this with Ruthie Halberstadt, who's on this call. We hosted this session at AGU last year about climate modeling for everyone, interdisciplinary research to address social justice and more than human impacts. And so, yeah, this is part of where I like to work. So the Paris Agreement, was the result of a multi-decade process within the United Nations. And so where I start in digging into some of this history is actually back in the 80s. But this here, I'm just going to go over the Paris Agreement is sort of the quantitative expression of the goal that was defined within the United Nations Framework Convention on Climate Change, which was adopted in 1992. So under the UNFCCC, it talks about the stabilization of greenhouse gas concentrations at the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. Whereas the Paris Agreement in 2015 has the languaging of holding the increase in global average temperature to well below 2C and to pursue efforts to limit the temperature to 1.5C above pre-industrial levels. And so this temperature target has become the quantitative expression of that term of avoiding dangerous anthropogenic interference. So by adopting global mean surface temperature as a global metric for international climate action, the conversation around risk and impact from climate change in policy spheres sort of became skewed towards this globally average version of one environmental stressor, which is the temperature. But that doesn't necessarily convey the breadth of impacts, which are going to vary geographically and are going to vary over time. There's also a discrepancy between danger as defined, and that's in quotes, this is quoting the work of Desai et al. in 2004, danger as defined by scientific and political assessment versus danger as experienced by communities on the front lines of a changing climate. So while climate change is of course a global risk, vulnerability is actually a locally experienced phenomenon, and systems of power and privilege will impact the decision-making process regarding what becomes an acceptable level of damage and risk. Often disadvantaging those with less privilege. Also, what is determined to be an acceptable risk is a bit ambiguous with respect to the concept of dangerous anthropogenic interference. And so to to do an assessment of the justice considerations here, I looked at three components of justice. So procedural, recognition, and distributive. So procedural is looking at power dynamics within decision-making processes. Recognition justice is existence rights of cultural and social groups, and distributive justice is an allocation of benefits and burdens of a particular thing. And so in this case, distributive justice is going to refer to the spatial and temporal variability of sea level rise. And so to do this, I looked through hundreds of peer-reviewed studies from across the fields of history, law, political science, physical sciences, sociology, a really broad range of literature, and then documents from the United Nations archives, and then centered the role of the Alliance of Small Island States, because AOSIS the AOSIS nations have been absolutely pivotal within the UNFCCC process. And part of their negotiation strategy has been to emphasize their impact due to rising sea levels. And so the centrality of that in their negotiating position and their strong history of advocacy within the UNFCCC led us to consider them first in discussing this. And so issues of justice are crucial in understanding the impacts of climate policy. And so I started out looking at procedural justice and sort of figuring out, well, how did we end up with a temperature target to begin with? That was not always the case. As you saw in the UNFCCC, it talks about stabilization of greenhouse gas concentrations in the atmosphere. So how did we get from stabilization of greenhouse gas concentrations through, of course, the Kyoto Protocol, and then on to having a temperature target with non-binding contributions instead of top-down binding emissions reductions? And there is an incredibly complex host of power dynamics that played out throughout that negotiating history that sort of pivoted us away from binding emissions reductions and towards this more amorphous concept of having a temperature target. And so I don't have time to go through how that all occurred. It has in part to do with the solidification of the neoliberal economic turn globally, and the strength of high emitting nations within the negotiation process, and the necessity of nations like the United States in being a part of that process, but them having very hard lines within the negotiating sphere of what they would and would not agree to in terms of a binding global commitment, or not necessarily binding in terms of emissions reductions, but binding in terms of the political process. And then as part of this, looking at the distributive justice aspects, that was assessing the spatial distribution of sea level rise. So this is a map that I created of the spatial distribution of the Antarctic contribution of sea level rise under RCP 8.5, using the Penn State University ice sheet model with no cliff collapse turned on. This is just looking at 2100. So the raw fingerprint data was provided by Jeremy Rothman and Natalia Gomez. And then I did the configuration of this map layout. And you can see the pink line here is where the Antarctic contribution is equivalent to the global mean sea level at that point in time. Everything above that is a higher impact. We know that factors impacting sea level rise have longer response time than just surface air temperature, and surface air temperature is depending mainly on cumulative emissions, and thus temperature is expected to begin to stabilize as emissions or CO2 concentrations stabilize. However, the sea level rise contribution is also very relevant to the time profile of the emissions. So you need earlier emissions reductions to really be able to mitigate some of the aspects of sea level rise. I'm running really low on time, so I'm gonna skip ahead a little bit here and just say that we did spatial statistics on the sea level rise Antarctic fingerprint contribution at various locations of AOSIS negotiating states to determine that they all have higher impact from the Antarctic ice sheet, which then is significant in terms of GMST and how GMST and negative feedbacks can interface with carbon budgets. While some feedbacks are accounted in some in some ways of doing carbon budget accounting. They are not currently included so far. And then the distributive justice feeds into the recognition justice, because temperature targets within this century are not telling us about the long-term multi-generational commitment to sea level rise and what that could look like long-term. Temperature targets have also brought with them a normalization of overshoot pathways, which we discussed earlier in the presentation. Overshoot pathways tend to encapsulate what is termed the political economy of delay, which is an attempt that sort of it's sort of a concept that characterizes UNFCCC negotiations and many other things as well, where there's a centrality of the economic impact instead of the actual human impact. And there are ways that negotiations have turned to looking at ways of meeting the Paris Agreement goals without necessarily reducing emissions in the near term. And we also have to remember that vulnerability is a locally experienced thing. And so in order to consider the climate justice implications of sea level rise, we have to consider colonial histories and what is impacting vulnerability at this point in time. We have to consider ongoing neocolonialism in terms of financial mechanisms under the Paris Agreement. We have to consider how power dynamics led to the entire situation that we have today and are putting different regions more at risk than others. But it's also extremely, extremely important to bring the voices of people who are not physical scientists and policymakers into the conversation more than they have been in the past, and to also avoid victimization narratives. Carol Farbatko coined the term the eco-colonial gaze to sort of characterize how we tend to talk about sea level rise vulnerability in island nations, which the eco-colonial gaze tends to be that the island nations and this idea of sinking nations is sort of a thing that we point at that then sort of tends to disembody the actual people living there. And when you actually look at what people on the ground are saying, they want adaptation in place. They have agency, they've had strong agency within the negotiating process, and the people living within states that are most vulnerable to sea level rise and need to have their voices heard in a way that they haven't been in the past. And so it's really important to consider all of these things and to consider how they play out in terms of sea level rise and in terms of climate justice and the Paris Agreement. So yeah, trying to summarize 11,000 words in 3 slides is never going to be sufficient. So I'm going to jump to the conclusion slide and wrap up in just a second. So temperature targets within this century are the goal for climate action under the Paris Agreement. And that is a result of a political decision that favored the interests of high emitting countries. But temperature targets do not capture other manifestations of climate destabilization, such as sea level. And temperature within this century as a metric itself has significant climate justice implications in terms of procedural recognition and distributive justice. And that's even in absence of the negative feedbacks. Those climate justice implications would be true either way. But they could be exacerbated by negative feedbacks and how that feedback on carbon budgets. So the spatial distribution of the Antarctic sea level rise fingerprint does put an excess burden on locations of AOSIS member states, but of course, that's going to vary geographically. Not all AOSIS states are islands, not all of them are low-lying islands. The geomorphology is very different, the socio-political context is very different, and not even just state to state, but within sub-local regions within a state. And so these concerns could become exacerbated if GMST feedbacks associated with ice sheet collapse raise carbon budgets, or if the Paris Agreement goals are not met and we are not on track to meeting them. So I hope that made some semblance of sense. It's a rather complicated argument to try to distill into a few slides. But thank you all for listening to these 4 parts of my presentation. Thanks to NSF for funding literally everything I do, to all of my incredible advisors, Ruthie Halberstadt, Ethan, Christine Shields, and Non Rosenblum, and literally everyone at NCAR for just being amazing and helping me get CESM up and running. So I'm going to stop share so I can see you all.
Thank you so much for a fascinating tour. Oh yeah, my mic is on.
Oh, I had a spelling mistake Thank you, Lawrence. Sorry about that.
Do we have any questions from the group?
I have a question. On one of the very early slides, you had something that I think was labeled as sea ice increase. Might have been one of your movies.
Yep.
Was that a sea ice production rate or a real map of what you
That
think
was a map.
sea ice? So how thick was the sea ice?
Really thick, like 10 meters in places. When we first saw that result coming out of the model, we were like, really? But yeah, it grows extremely thick in certain regions. If you go look at the paper later, it's talked about in a little bit more detail, but yeah, it's 10 meters in certain locations. So much different than what happens today.
Do you think that's realistic, or is that because you're putting the fresh water out too much at the surface, or what? Because it's important, right? Because it feeds back into your surface temperature. Yeah.
Yeah, absolutely. So yeah, I was talking with some folks at NCAR about this, about whether or not the sea ice response was physically realistic. And it's really hard to tell, because of course it's also just with one model. But other models have shown sea ice growth as well. I don't know if the thickness is physically realistic or if it's not, but the albedo feedback is more on the area than the thickness. And so I think if the spatial area is also rather large, then the albedo feedback will be rather large as well. But I do think overall in that first study that with the methodology, it's hard to say whether or not that methodology is going to match reality, because what we're showing with the preliminary results of the coupling runs is that things are going to look a lot different if the ice sheet model and the climate model are going to be able to communicate with each other. So I'm interested to see what we get in terms of sea ice growth and global mean surface temperature response in the coupled run, and then comparing that to the older run and using that as a bit of an assessment to see how reasonable that is.
I assume the model also gives the velocity of the ice as it gets thicker, so you could see whether it was slowing down or whether there's some feedback in the dynamics that was leading to a sort of land fast, really thick ice in front of the ice shelves.
That's a really good point. I will check that. Thank you.
It was a great talk. Thank you.
Thanks.
Thanks, Laurie. Do we have any other questions from the group?
I have a question. Does any part of the new IPCC report change the analysis of your justice component?
So I haven't had time to read it yet, but that is on the list for this week. But yeah, I will get back to you in lab meeting, Ruthie. Or we can meet up on the side and discuss it after I have time to read it.
Thanks, Ruthie. Do we have any other questions? Final questions, perhaps. We're ever so slightly over time here. I'm conscious that some people might want to go to other meetings. Are there any other questions? Nick says, thank you. Great talk.
Thanks, Nick.
Thank you.
Thank you. And yeah, reach out.
Okie doke. I think people are signing off now. Thanks again ever so much for presenting such an interesting talk. I really look forward to putting it up online.
Thanks. Thanks for having me.
Thanks everyone for joining us this morning. I hope you have a great rest of the day. Bye everyone.